So, good afternoon, Akshay, Arjun. I hope my screen is visible and audio is clear. Okay. So, okay. So, in case if you face any difficulty in hearing or something, you can tell me. So, welcome to discussion session 9 on our natural convection heat transfer and diffusion mass transfer. So far we have actually covered, we have covered the introduction to free convection, analysis of free convection, etc. And in the previous lectures, we have been through diffusion mass transfer and its mathematical analysis. After that, we went for some problem discussion session initially. Now we will have the problem discussion session 3 today. Some important problems. So in diffusion, actually, some problems are of, most of the problems are of kind of repetitive nature in some senses. So we will limit us to some important problems in this related to diffusion. So after that, in the next sessions, we will be discussing operation and we'll be having a problem discussion session and we will just summarize everything. So whenever you study this diffusion, you should always correlate with our heat transfer. Then analysis becomes more easy. It's almost similar. Like however, we can see that free convection is somehow related to diffusion mass transfer in the sense that free convection occurs due to the temperature difference, which causes the variation in the density, and that is driving the flow. But in diffusion-based mass transfer, what is happening? The concentration is different. So the concentration means it's also the density different, but it's due to the difference in the moles. So it's a difference in the moles at a particular point. So that difference is actually guiding the flow in diffusion mass transfer. Okay. So today we'll be having the problem session 3 discussion. So let us go to the question 1. So today I will be discussing this session through, so my writing pad is not there. So I will discuss three important problems in our textbook problem. So we will discuss that session and for today's part. Okay. So these are the important problem. Like the first question, a common procedure for increasing the moisture content of air. So if you want to increase the moisture content of air, is it to bubble it through a column of water? Okay. So assume that air bubbles to be of spheres of radius 1 mm and it is to be in thermal equilibrium with water at 25 degrees Celsius. So the question is, how long should the bubbles remain in water to achieve a vapor concentration at the center that is 99% of the maximum possible concentration? So it is given that the air is dry when it enters the water. So we have the data, radius is 1 mm, water is at 25 degrees Celsius. So from the tables, we can see the binary mixtures in this problem are DAB. So determining the diffusion coefficient, the binary mixtures are air and water. So at a particular temperature, you can determine this value. So if it is 25 degrees Celsius, 1 atmosphere, you can determine the UV value. So the question is, how long? How long should the bubbles remain in water to achieve this vapor concentration? So what does how long means? It's a time. So it's definitely a transient mass transfer problem. So the vapor concentration is achieved to be 99% of the maximum possible. So you can see here the transient diffusion equation for a one-dimensional transient diffusion equation, and that is having a constant DAB value. So for a constant diffusion coefficient, this is the 1D equation. Okay. So it's similar to the heat transfer. You can see that is similar to a heat transfer problem. So the initial concentration that is actually shown here. So at x0, which means that at time t equal to 0, the concentration is CAI. Okay. So initially the concentration it is said that it is dry when it enters the water. Okay. So dCA by dx is 0, which means that there is no spatial variation or along the x direction in which the water is entering, there is no variation. So CALT. So these are the boundary conditions of a general transient diffusion equation at a particular distance. So these are the general form. Now we should apply that to our problem. So this question could be well understood if we understand the analogy between heat and mass transfer. So to solve this problem, one approach is introducing a dimensionless concentration and time as follows. So this is a dimensionless value. So it has no unit. It is a ratio of gamma by gamma I. What is gamma I? Gamma I is the concentration difference at the start of the problem. And gamma is the concentration gradient at a particular point of time. Okay. And Tm is the time required for the mass diffusion. And the star denotes that it is non-dimensionalized. So it's a procedure to non-dimensionalize. So if you note the value, you can see it is having DAB into T by L square. Okay. So DAB is, the unit is meter square per second. This is time is having a second and L is having meter. So that is coming to be meter square by meter square. So it is dimensionless, which is actually called as the Fourier number based on mass transfer, denoted as FO underscore n. Okay, so Fourier number. Fourier number in heat transfer is alpha T by L square. Okay, here it is DAB into T by L square. So there the diffusion coefficient is the thermal diffusion coefficient or the thermal diffusivity alpha. Here, what is that? DAB is the, what is that? DAB is the diffusion coefficient. Okay, so just plug in these things into here in the main equation. You can see from this value, from 14.81, if you substitute it into the general equation, it becomes in this format. You can just see that. Okay, so you will get that value, and it is mentioned as this x star. X star is just a non-dimensionalized procedure, so just replace x by L. So one important aspect of non-dimensionalization, as I said in the Nasural convection part itself, it can be applied to any geometry. So just we need to give the non-dimensional factor into any geometry so that we can easily solve it. So that is the importance of non-dimensionalization. And the initial and boundary conditions for this, suppose this boundary condition can be modified like this. You can just check it. So at any point of time, so anything that is coming is conveniently modified in terms of gamma star. So the second factor gets modified like this, and third factor gets modified like this. Okay. So coming to our problem. So the question is, we assume that there's a one-day radial diffusion of water vapor in air, and there are constant properties of air, and the air is initially dry, and it is a stationary medium. Okay. So okay. So coming back, so the question is the time taken to reach 99% of the saturated vapor concentration at the center. So whenever we are writing, I suggest you attempting these problems, you just state out all the assumptions you have taken. Just draw a schematic diagram. So air is coming, and it is the bubble is having a radius of 1 mm, and it is having a concentration CAS. From property table, we have determined the diffusion coefficient value. Now, the solution to the problem, the previous case. So this solving this problem, we will be having a solution which is having an infinite series problem, because it is in terms of x as well as t. So you can see there are time as well as x. So that derivation I am not doing. It's a bit lengthy derivation, but you can refer to that. It's like an expansion series, like in a diffusion problem. Even in conduction, that also there. So so there will be n number of terms for that. So the what you are getting is this is the heat transfer in heat transfer, which will be there in our heat transfer. So theta 0 is a dimensionless value. C1 is a constant, and this is exponent e raised to minus zeta 1 square into FO. That is in actually heat transfer. So similarly, coming to mass transfer, the same equation modified in terms of concentration. So that factors will be modified like this. Gamma O star is equal to C1 exponent minus zeta 1 square into FOM. So this is Fourier number based on mass transfer, which is DABT by L square. So the question is like, how much time will it take to reach 99% of the saturated vapor concentration in the center? So our expression can be modified. This gamma O star, as I said previously, this is actually Ca minus Cas by Ca minus Cas. So here that value is actually this. So this is coming out of a solution. So there are n number of terms in the solution, but we will take the first term. Okay. So that's why it is denoted as nearly. So there are n number of terms, but we neglect it in magnitude. The first term is bigger. So it is 5 plus 0.5 plus 3 plus 0.3, etc., etc. So we assume that the first term, or it's actually the first term which is bigger. Okay. So that's a reasonable approximation. Otherwise, we have to solve for the entire value, C1, C2, C3, etc. But if you take the first term, that analysis becomes very simpler. Okay. So the question is, at any point of time, we need 99%. So Ca, that value is 0.99. CAS, so that is a saturated value. That is 1. And it is said that the air is entering dry. So at initially, there is no concentration of water. So that is 0. So when you substitute that, you can see that gamma O is equal to 0.01. And the C1 value you can get from the, there's a chart for this solution. This is an infinite series solution, and there are some charts available for that solution for different cases. So it's a mathematically, these constants are obtained by solving the Fourier series. So there are values already available, like in our logarithmic table and all. So C1 value comes to be 2, and zeta 1 value comes to be 3.145, for which case Biot number based on mass transfer is tending to infinity. So what is that Biot number based on mass transfer? It is similar to our heat transfer, but that Biot number based on mass transfer is alpha T by L square. So here that is that difference. Okay. So you can see that all this in the table, actually the table is there. You can just refer. So it is not shown here. Refer to that. You can see all these C1, zeta 1 are corresponding to a Biot number. Biot number based on mass transfer. Similarly, in heat transfer also we have this thing. Okay. So when you refer to that as Biot number, this Z1 and zeta 1 are mentioned. So here we have taken this Biot number to be infinity. Why? Because we think that it is happening over a large period of time. It is happening over a large period of time, so that Biot number, which is maybe alpha T by L square, here it is DAB T by L square, that becomes bigger. So for a large time period, this Biot number, you just understand that it is signifying a large time period. Okay. So that becomes easy. So just substitute that values. 0.01 is here. Then 2, that value is here. And that zeta 1 value is here. From that, you will get the Fourier number based on mass transfer. So previously, I have said Fourier number based on mass transfer. What is it? It contains a DAB T by L square term. Okay. So we need to determine the time. So the unknown factor is this time. So from that, we will be getting. So here you see this DAB T by L square is for a pipe or a long plate or something. Actually, that is LC, which is the characteristic length. Suppose if the geometry is changing, this L value changes. In a kind of a sphere or a bubble or kind of thing, that characteristic value is diameter. So if you substitute that, that becomes a diameter. Okay. So just substitute that value is Fourier number based on mass transfer into d square by dAB. So when you substitute that, that value becomes 0.02 seconds. So you see Fourier number based on mass transfer. So so we also see a comment from that Fourier number is greater than 0.2. the approximate solution is valid. So these kind of solutions are called as approximate solution. So you have seen in I think the transient cooling of a kind of a sphere in air or something. So in that similar kind of, we mentioned about the Fourier number based on heat transfer. So there we will check that Fourier number is actually less than 0.1. So what is that kind of analysis called? Any idea what that analysis is called in that transient cooling of solid in air? So we will check the Fourier number. So if Fourier number is less than 0.1, we will call it by a particular analysis. What is that analysis? Anybody knows? You can just leave in the chat. So question is that Fourier number is less than 0.1 in heat transfer. And suppose we are keeping a sphere, allowing it to cool in air at a particular temperature higher than the air, maybe 60 degrees Celsius. So gradually the sphere will get cooled down. So in that analysis, we will first check Fourier number to be less than 0.1 for the analysis to be valid. So if not, any idea of that? What type of analysis is that? So I'll just leave in the chat. That is called as a lumped system analysis. So you can just refer to that. It's a transient cooling. It's in the convection problem that is there. Lumped system analysis. So that kind of analysis, lumped systems, where we assume there is no spatial variation in the heat transfer or something. There we will be considering the time-based cool. So we'll assume the temperature at every point or any property at any point inside that substance to be same. So the temperature will be only a function of time. So that such kind of analysis has to be valid only when a particular condition is satisfied. So here in mass transfer, for that to be valid, Fourier number has to be greater than 0.2. So it's a kind of an analysis that we can see. So another question could be asked like, find the radius and temperature. So question can be maybe if it is 95% of the maximum average vapor concentration, how will we determine? If it is 50%, how will we determine? So then also the procedure is same. See, in that case, we will be using this same expression, C1 exponential minus E square, that condition. And similarly, we will here. So here, what is the change? CA will be 95, so it is 0.95. In the second case, if 0.5, so that will be the case. So if you are taking, say, in this analysis, what difference is? One term approximation we have done, which means the first term in that approximate solution is done. Okay, so here they have shown that concentration directly that equation. So this is in terms of the zeta 1. So they have removed all that and expressed in terms of zeta 1. So that's an alternative mathematical formulation. You can resort to the same previous procedure and see. So only difference is CA changes to this one. So you can get a plot of that maybe. So initially it was at a higher temperature, the graph will come slowly downwards. Isn't it? Or is it upwards? It's not in cooling problems and all, it is downwards. Here it is a concentration. We are adding moisture into it. So initially air is dry. So it will be on a y-axis. From there, it will gradually increase and it reaches the saturation value. So the curve will rise upward. And that varies with time also. Okay. So in this such problem, you can see there is one comment, the time associated with an average vapor concentration of 50% is expected to be significantly shorter than in part A. So hence that Fourier approximation less than 0.2 and one-term approximation to the exact solution may not be valid. Okay, so you see that the time, so here we have assumed that assumption, right? So to reach that condition. So So you see that one problem is there. So here we have determined that time required to reach 50%. So see, it is 9.7 millisecond. What is here? 0.02. So it is saying that the time required to be 50% is very less than. So suppose to reach from 0 to 50, it is taking only 9.7 millisecond, which means 0.0097, which is actually shorter than the time taken to reach 0.02. So here, when it comes to the smaller concentration, that one term approximation is not the case. So there we have to take multiple terms. So it can only be said after analysis. So when it is large concentration of vapor and mass transfer happening, you can just use this equation. But when it comes to using lesser concentrations, 50%, etc., maybe half of the maximum value, that one term approximation is not valid. So that will give a wrong value, and we will proceed with that. So we need to be very careful when we are using such approximations. Okay. So let us move on to question 2. So question 2 is, if an amount of energy is released instantaneously, for example, from a pulse laser, and is absorbed by the surface of a semi-infinite medium. So this term is actually new to you. Semi-infinite medium is actually a term which is actually meaning that suppose if you take a kind of a wall or a kind of a large body, maybe we can, the good example is our Earth itself. Okay, in our Earth actually, the proper definition is like any substance which is actually very large compared to its one other dimension. Okay, so it's called as a semi-infinite medium. So it is extending to infinity in one direction, which means that any kind of signal, heat input, or any kind of input given to the system, that effects will vanish after a particular length. Suppose if you take a particular kind of a wall which is very thick, and we supply some heat to its outside. So as soon as the heat enters, you see that it will only penetrate up to a particular length. After that, all that effect will lose. So it will gradually diminish. So after a particular length, there is no meaning in actually conducting the study. So such mediums can be said to be semi-infinite. So in this question, that word is used because just for it understanding, so that it will be having a significant losses or some kind of a penetration length for that. Okay. The question is from a pulsed laser, maybe it may be used for a machining process. Okay. So what is happening is TA is the initial uniform temperature of a particular medium that is subjected to a pulsed laser. So consider an analogous mass transfer process involving deposition of a thin layer of phosphorus on a silicon wafer. So in the manufacturing of this silicon wafers and all, we will coat phosphorus on it, right? So it is like a silicon wafer is there, then it will be dipped into a gas of phosphorus. So there will be a concentration difference and phosphorus starts depositing on the surface. So this will be at very high temperatures and all maybe. So the question is, if the wafer is placed in a furnace, the diffusion of P into silicon wafer is significantly enhanced by the high temperature environment. Okay, so the question is, a silicon wafer with 1 m thick, it's actually micrometer. Please note, it's not 1 meter, it's micrometer thick. Phosphorus film is suddenly placed in a furnace at 1000 degrees centigrade. And the resulting distribution of P is characterized by the expression of the form. Okay, so Cpxt is equal to MPO. So what is that P? P just means the concentration. So it is mentioning that the concentration of the distribution is denoted by this expression. So this MPO is a molar density. Cp associated P just means that it's phosphorus. Okay, concentration of phosphorus. Don't mistake that it's specific heat. It's just a concentration of phosphorus. Okay, and thickness DO. So this is the expression. Okay, so heat is applied So initially it is at a particular, that film is at a particular temperature Ta. Its thermal properties are rho C K. And you can see that curvature. So it is at a different instance of time. See, as the time increases, what happens? As the time increases, so here in this direction, time is increasing. It is just flattening. So initially it was this curve. Then later it changed to this curve. Later it changed to this curve. So it is the temperature curve versus X. So the question is, explain the corresponding difference between variables in the analogous temperature and concentration distribution and determine the mole fraction of phosphorus at a depth 0.1 micrometer, it's micro, in the silicon after 30 seconds. So the diffusion coefficient value is also mentioned for phosphor-silicon combination. So here the diffusion is happening between the binary mixture phosphor and silicon. So that value is given, and mass density, so the density values are also given. So what is mole fraction? As I said, mole fraction is the ratios of the concentration. Okay. So, and what is mass fraction? It's a constant of the densities. So molecular weights are also given. So this is a transient problem. For a transient problem, we have to determine the mole fraction. So that's a question. But the one change is here is that concentration is function of distance. It's not constant. It is varying with respect to the thickness of the film X. Okay. So this is similar to before that. We will just look at. So here there is one case here. So I will discuss that immediately. We will see how that is related to heat transfer and mass transfer analogy actually. So this is one another question where thick plate of pure iron at 1000 degrees Celsius is subjected to a carburizing process with sudden exposure to carbon concentration. So in manufacturing process and all, these are very important. So in a large furnace, this will be immediately put. So due to the concentration difference, that will be deposited. Maybe you might have heard like it in like carburizing process and all, anodizing, etc. So consider the heat transfer analog to carburization process and determine. So the question is that, so we'll assume an analogy like this. So I just mentioned this to understand that there are some similar phenomena happening like this. Okay. So we will see an analogy between heat and mass transfer. So heat transfer distribution, this is the equation for a semi-infinite medium, where we will consider this as the penetration for a particular temperature. For mass transfer, that will get modified like this. So the flux also, it will modified like this. So this concentration, in terms of concentration and molar. So these are the expressions that will come useful. Okay. So for our question, so it is mentioned the temperature distribution is set here and it is exposed to an amount of Q double dot. And determine the mole fraction question. So 1D transient diffusion we assume, and wafer we approximate it as a semi-infinite medium. So we can use these expressions, semi-infinite medium. So you can see that T is actually related to X as well as time. See that analysis? The time is connected to the distance as well as time through a single expression. Here also you can see the concentration is related to distance as well as time. So both parameters are coming here. So that's the beauty of this analysis. Okay. So what we will do is here Txi minus Ti, we will substitute given it like this. So thermal process, it is given. Here it is given as a function of this expression. Okay, so that is given. So, so just to understand, you can see that correlation, the understanding between temperature and concentration difference. Okay. So the molar density associated with the thickness of DO. So here it is 1 micrometer. So what is X? What is X? Yes, X is actually question. What is it is asked? In the question, it is asked at a depth of 0.1 micrometer. What is the mole fraction? So the vapor would have been coated there. There will be phosphorus vapors inside that at a point. The total film thickness is 1 micrometer. And we are asked to calculate the vapor fraction or the mass fraction at a depth of 1/10 of it, which is 0.1 micrometer. So MPO, which is actually the mass phosphorus, so that flux, so that is actually concentration at XO DO into DO, that thickness. So that is actually density to mass ratio. Substitute that values, and DO is that film thickness. You substitute, we will get the mass, total mass kind of flux into the surface. Mass flux into the surface. See that analysis. Q0 is the heat flux into the body. Here, what is the similar term? We are supplying the phosphorus flux into that silicon wafer. So what is the mass of the silicon flux into the, phosphorus flux into the silicon wafer? That value is actually shown here. So this is the amount of flux which is acting per unit area into the silicon wafer. So we are asked to find that at a particular depth, what is 0.1 micrometer and at 30 seconds. So simply substitute in that, you will get the concentration at that particular point. So you will get that value, and from that concentration, we know mole fraction is the ratio of the concentration. So concentration of phosphorus we have determined 1.85, and concentration of silicon, so that is rho SA by MSI. Okay, so that we will substitute and we will get the mole fraction. So this has come from a kind of a transient analysis. So here you see the concentration is a function of this time as well as distance. So we have already been supplied with this equation. We just need to substitute that value for, first find the mass flux. We have all these values. We need to find that particular point of time. So this is actually the graph you can see for time. If you give some random values of that, you can see that graph is coming like this. Okay. So the last problem, I think this problem was previously discussed in the last classes, like garment is soaked with water and hung up to dry in warm at atmospheric pressure. The still air is dry and at a temperature of 40 degrees Celsius. The garment is assumed to have a temperature of 25 degrees Celsius and the characteristic length of 1 meter in the vertical direction. And we need to determine the drying rate per unit width of the garment on the rate removal from the water garment. Okay. So you can see all these analysis. So I suggest you to go through all the mass transfer as well as heat transfer. We have discussed heat transfer correlation. So go through all the heat transfer and mass transfer correlation. So and understand their similarity. So the only the so to go through all this, and you can see how it is related. So this problem is also having one another interesting correlation. It's a very simple problem. We need to determine how much water will be dried through this soaking up water in the air. Okay, it's a very interesting problem. Okay, so we know the wet garment which is hanging at 25 degrees Celsius in a still at 40 degrees Celsius. So we can approximate this garment to be like a vertical wall at 25 degrees Celsius, and water will be evaporated and the air is still and dry. So this is a vertical plate-like analysis. So we will apply the heat and mass transfer analogy, and we assume that that is fully saturated, soaked in water. We assume the perfect gas behavior of water, vapor, and air. So this is a mass transfer problem. So essentially, we will find what is the amount of drying rate. Okay, so it is like a problem. And what is a binary mixture here? Diffusion coefficient is the air as well as water. So air, the approximate temperature, so properties we need to determine first, the thermal properties and fluid property, kinematic viscosity, then pressure of that saturated state at that particular temperature. So that is 0.031 bar, and density, which is equal to from the table we can determine, and For air water vapor mixture, the diffusion coefficient is here. And as I said, Schmidt number, which is an important parameter. So 0.607. Okay. Schmidt number is similar to our Prandtl number in heat transfer. You know, Prandtl number is the ratio of nu by alpha. So Schmidt number is the ratio of nu by diffusion coefficient. So what we need to determine is the drying rate per unit width of the garment. So the mass removed is equal to HM into L into rho AS minus rho infinity. So do you see a kind of a similarity here in this analysis? Yes. So we know heat transferred is equal to Q is equal to HL delta T. Similarly, mass of the water removed from the garment is equal to the mass transfer coefficient, similar to our heat transfer coefficient, into the length. It's actually per unit width. That's why it is L. Otherwise, it would have been area. Then the difference of the concentration, which is the density difference. So if we know that value, we will simply get how much water will be removed per unit time or unit width. Because this will be having an unit of per second, and this is per width. So that we will be getting. So we need to determine HM, rho S, rho infinity. From that, we will get how much will be the. So how did we determine the heat transfer coefficient H in natural convection? We use the Nusselt number, right? So similarly in mass transfer, there is another number that is called as the Sherwood number. Sherwood number, which is actually connected with Grashof as Schmidt number, similar to our Grashof and Prandtl number. So this is the correlation. Okay. So if you determine that, we will get the Sherwood number. From that, we will get the HM. So how will we get that? We will see. It is also similar to natural convection heat transfer. So as I have said, this is a convective mass transfer kind of a problem. Okay. So this is convection related mass transfer problem. Okay. So the drying rate per unit width of the garment is this expression. So already we discussed, this is this expression. So we need the Grashof number with respect to characteristic length L. So in heat transfer, we know natural convection Grashof number is G beta delta T LQ by nu rho, right? But here there is no delta T. Delta T is actually that has come from Bosnia's approximation. That's why G beta had come there. But please understand, in this problem, there is no beta delta T. Instead, that will be delta rho by rho. So there is a density driven flow due to the concentration difference. Density driven flow due to concentration difference. In natural convection, what is that? Density driven flow due to temperature difference. So density difference is rho s minus rho infinity. So at the outer air, there is a particular humidity. On the surface of the cloth, there will be a particular humidity. So there is a difference between them that is actually guiding the flow. So that is the major factor. So it is not that it is always there in a natural convection. Actually, both will be there, but we assume that this is much more significant. So that that factor is more significant. Okay. So the still air is dry. So rho infinity, which is the surrounding air humidity, is equal to rho B. B stands for the still air condition. So that is actually, it is mentioned as the outside air is dry. So PB infinity by RB into T infinity. So RB value we can determine. So PB infinity is 1 atmosphere and rho infinity is also given. So from that we will be determining the density of the air. So that value would come to be 1.1280 kg per meter. So next is density of the air or vapor mixed at the surface. That is actually rho s is equal to rho as plus rho bs. And with PBS is equal to 1 atmosphere minus PS, which is actually the pressure of the air. Total pressure we know. So the mixture is actually air vapor mixture. So if you know the density of that, you can determine the other factors. So pressure of that is actually of the dry air is total pressure, which contains vapor plus air minus the vapor. So we will be getting the net pressure. So we will be getting the saturated, the density of that. So PB infinity. So we will be getting that. So that value is 1.1477. And rho S, as I mentioned here, it is a sum of, so this is an approximation kind of thing, sum of the densities of the vapor and that dry air part. So that we will get. And rho is equal to the average of that value. So here we know delta rho. We need that delta rho value, which is actually rho S minus rho infinity. So one side there will be, it is like our Ts minus T infinity. So for that, we will be determining the average value, the bulk fluid temperature. So here similarly, we will be having the bulk density. So that value is determined. From that, we can calculate the Grashof number. So Grashof number is coming to be 1.467 into 10 raised to 9. Understand that this is due to density difference. Okay. So from that, we will be getting the Grashof number into Schmidt number. Schmidt number is also there. So this here. So you can see it is more than 10 raised to 9. So we will be using this correlation. That's why we have used this correlation. So see here, Nusselt number we will be determining, and from that we will be determining the heat transfer coefficient. Now mass transfer coefficient we will be determining similarly. So that will be HM from that. Here in that you just see heat transfer coefficient H was NU into K by L. Similarly, it is here, it is dAV by L into Sherwood number. So that will be this value. Please note that this is meter per second. It's not velocity. It's that per unit length. It should have been meter square per second. Okay. So the drying rate is simply substitute that 2.75 into 10 raised to minus 3 into 1 into 0.0226. So that will be 6.21 into 10 raised to minus 5 kilogram per second per meter. So that is per unit width. So at any second, this much amount of moisture will be removed. So there is a very less like under this condition. So you can check if the temperature is changing, increasing, how much it will change. So if you increase the temperature, how much that variation would come to. So since rho S is greater than rho infinity, the buoyancy driven flow descends along the garment. So it is not an upward flow. So rho S is actually, as I said, it is greater than rho infinity because it's a denser, the saturated, the garment is saturated in water. So it is actually having more density or more concentration. And infinity is very dry. So all the flow will be like from top to bottom. If we have rho S is greater than infinity, so the mass will be removed upwards. So it's like the moisture removal is happening. It is similar to that of a cold plate kept in the case. So the mass transfer happens. There will be mass transfer in cold plate. That's the case. And similarly, here it is mass transfer. So you can just try out for different garments how much moisture will be removed. Depends upon how the fabric is actually causing that thing. So if the fabric changes, what factor change? If you can see, if the fabric changes, the diffusion coefficient will be determined. So that all factors are not essentially considered. So it depends upon the fabric also. It is nothing is mentioned. This problem simply states that it is a garment. If it is a cotton garment, if it's a polyester, different types of garment will be having different drying rates. So the better drying rate, better would the cloth dry, and it would be useful for our processes and all. So this is a direct application of our daily usage. Okay. So today we'll be stopping at this, and in the next session, we'll be discussing on evaporation and sublimation and some problems, and we'll be discussing analogy and heat and mass transfer. We may be winding up in, if possible, in the next 2 classes. By that, we will be summarizing everything with some problems, and we can have any doubts or anything clear. and that will be useful. So we'll be covering up the natural convection as a heat transfer as well as mass transfer aspects. Hope it is clear. If there is any doubt or something, you can ask. Okay. So I hope that it is clear. So just see you in the next class. See you next Sunday. So we'll be discussing the final part. Thank you.